Okay, let's start our class today with the session of Umul Kitab Al-Fatihah. Okay, in previous class we talked about what? We talked about conductor. In previous class we talked about conductor. Okay, and we say that metal is good conductor. However, material doesn't need to be a metal in order to conduct. So the first thing is that material. Kenapa color macam ni? So the first thing is that metal is good conductor. Metal is good conductor. Good conductor. But what we call you don't need to be metal in order to conduct electricity. It just happened that inside this metal, you have electron that is free to move. You have the electron that is free to move, free to move, and because of that, it's easily conduct the electricity. So the electron here. So we talk about electron a little bit. So the electron carry with it the charge. Electron carry what we call charge. Okay, for the electron, the charge amount is 1 is 1.6 10 to the power of negative 19 Coulomb. Okay, so the charge for the electron is 1.6 times 10 to the power of 19 Coulomb, and because electron carries negative charge, so you normally see there are negative there, negative in front. So the negative is just to say that this is negative charge. Okay, so electron carry charge of negative 1.6 times 10 to the power of negative 19 Coulomb. Likewise, the proton also is a charged particle. Okay, so the proton, if you have proton is also a charged particle. It's a charged particle also, but in this case, it's a positive charge. The difference is that they have a negative charge, but the magnitude is same like the electron, 1.6 times 10 to the power of negative 19 Coulomb. Okay, so this is basically what we call both proton and electron have a charge. The magnitude is the same, but the sign is different. Proton positive and the electron is negative. So you might ask, what is this Coulomb? Coulomb is basically the SI unit for the charge. Coulomb is a SI unit for the charge. So if let's say one electron have this 1.6 times 10 to the power of negative 19 Coulomb, so that's mean 1 Coulomb. So let's say I put here 1 Coulomb, meaning that what? Meaning that you divide by the what we call you just divide by 1.6 lah. 1 Coulomb 1 divide by 1.6 times 10 to the power of negative 19 lah. So in order to get how much electron lah. So this Coulomb, so that's why you can cancel lah. You can cancel this and this. Cancel this. So you know how much electron, because 1 Coulomb is, so if on the top is electron. Okay, so 1 electron carry 1.6 times 10 to the power of negative 19 Coulomb. So you forget the negative part. Negative is just the sign only. So you do this thing, you will get what? You will get for the electron, for 1 Coulomb, you will you divide this thing, you get what? 1 divided by 1.6 times 10 to the power of negative 19. You get 6.25 times 10 to the power of 18. 18. And what is that? That is electron. Electron. Meaning that in 1 Coulomb, you have what? You have this thing is 6.25 19, so meaning that million electron. So what does it mean? So that's what does it mean by 1 Coulomb of thing. It's just like a mole. Mole is just the amount of something. 1 dozen is 12. 1 mole is 6.23 times 10 to the power of 20 whatever. And then 1 Coulomb is basically this. 1 Coulomb is the amount of electron or whatever charge lah. In this case, we talk about electron. If it's proton, then it's proton lah, because the magnitude is same. So 1 Coulomb is 6.25 million electron, the amount of electron. So that is 1 Coulomb lah. 1 Coulomb. So in everyday life, you don't really heard about the Coulomb. Normally, you see when you talk about the electricity, let's say I put here, when you talk about the electricity, one of the properties of the materials is electric, whether it can conduct electricity or not. Whenever you talk about electricity, normally you heard about what? You heard about the voltage, you heard about the volt or voltage lah, voltage, and also the current, current. So V, and then current is ampere. So the voltage is basically the electric potential lah. The voltage, the other name for that is so the other name for this is electric potential lah. Electric potential. So basically the voltage is basically the potential over 1 coulomb. The potential energy over 1 coulomb. Let me put the current down because I don't want to confuse this thing. So I put this down. Okay. So voltage is basically a potential energy per 1 coulomb charge. So so energy normally you what we call the energy, normally when we talk about energy, normally we talk about joule, something like that. Something like joule, like that. Example of energy is joule, the term, that the unit that normally you heard. So basically 1 volt, so meaning that 1 volt is basically 1 volt will give 1 joule of energy for every 1 coulomb lah. For every 1 coulomb pass through lah. So if let's say I have battery, mana battery saya? Alah, battery ni dah leak. Battery ni leak. Okay, this one battery, let's say this 1 volt or this is 1.5 volt, right? Normal battery. So the energy that this battery give is basically 1 joule for every 1 coulomb. You know 1 coulomb is that million of electron pass through this thing. So that's the idea for this volt lah. What does it mean by 1 volt? So okay, let me go down. So this we put here. So that is 1 joule of energy. But then you might ask, what is joule? And what is joule itself? Joule is what we call, joule is the unit for the energy. So let me put here. Joule is basically the unit of energy. But the question now, how much is 1 joule? Because the voltage, you can see the voltage somehow like this. This is 1.5 volt, like that. But then the definition of 1 volt is that the energy over the coulomb. So 1 joule of energy per 1 coulomb. Now you want to ask, what is exactly the joule? I mean, joule is energy, but then how much is this 1 joule? How much energy constitute 1 joule? So in order to know that, because I think I discussed this because the term energy is, you will meet it many times during your course of chemistry degree here in URA. For example, when you deal with the thermodynamic, you talk about the joule also. You do your IDP, you will talk about the joule, the kilowatt, and so on. So joule is 1 unit that is you will meet again and again throughout your study. So you need to sort of like get some intuitive what we call feel how much 1 joule. 1 kg, you can feel it. How much 1 newton? You see 1 newton, you have an apple there. This apple rests on my hand. They are like gravity acceleration down. So this is 1 newton. But what is 1 joule? What is the amount of joule? Okay, when you go mana ni? Saya duduk sini sikit lah. Saya nak buka ni. Okay, so in daily life, you often see when you buy something like this. Nampak tak? Saya buat zoom lah. I don't know where I can zoom. When you buy something, you go to the ingredient part, you will see there is, nampak kan? So tak tahulah jelas ke tak. It's not sharp, whatever. But you can see the energy there. They normally put joule. I don't know whether you can see or not. Is it okay? Whatever. but let me read for you. So there they said that for 100 ml they have this. So when you see that thing, they said that mana ni? So the I kotak tu, in the ingredient part here, you will see that it said that for 100 ml, so whenever you consume 100 ml, you basically consume 92 kilojoule and 92 kilojoule, and then they put in the bracket 22 kilocalorie. Okay, so this what you see in this kotak lah kalau you tak nampak. So what does it mean here? Joule and calorie more or less related lah. So calorie is just another way to talk about energy lah. Normally when you buy something, the food or whatever, they talk about in term of calorie. So 92 divided by 22, you get around 92 divided by 22, you get around 4.1 lah. Around 4 lah. 4. So meaning that 1 calorie, so meaning that 1 calorie, mana ni? 1 calorie, meaning that 1 calorie sekejap nampak tak? 1 calorie equivalent to 4 joule. So that's what does it mean. Tak nampak dah. So tak apalah, saya tutup ni dulu. Biar saya tutup dulu. Okay, so you see 1 calorie equivalent to 4 joule, but still it doesn't tell you how much this 1 joule, right? How do you feel this 1 joule? You just know that 1 joule equivalent to 1 calorie equivalent to 4 joule, but how to feel that 1 joule? So basically 1 joule is basically the energy required, to, so 1 joule, so if you see the definition for joule itself, 1 joule is basically 1 joule of energy is equivalent of you moving what we call 1 Newton force over 1 meter lah, 1 meter. So basically 1 joule is basically 1 joule energy is equivalent to when you exert 1 Newton force over 1 meter. So for example, let's say do I have this thing? Let me put there. So for example, this, let me make it out zoom first. Go here. So you know this apple, right? This apple is 1 Newton. Apple is 1 Newton. We learned before roughly the weight is 100 grams. So when you put on the table, so this apple, the force down, bring it down is around 1 Newton. So in order to raise this apple, you need the force more than 1 Newton. So if I bring this apple 1 meter up, meaning that I'm using 1 joule. So that's what does it mean by joule lah. So the energy that you use to bring this apple from this state up to 1 meter up, like that, 1 meter or whatever that, 1 meter. So you are using 1 joule of energy. So if you look this apple also have some energy inside. So if you go to Google, the apple, let's say I go there, apple, you nampak kan? Apple calorie. So if I write that, mana ni? Dekat sini. Okay. You can see that the apple have around 52 calories. Roughly for 100 gram apple, you get 52 calories. So what does it mean is that if let's say this apple, so let's say I draw the apple here. So I draw the apple here, apple there, and then this around like let's say 5 calorie, 5 calorie, 50 calorie. Let me draw this. 50 calorie. So if let's say 50 times 4, so you get 200 joule. So meaning that if let's say I have this apple and I eat this apple, let's say 100 gram, 50 calories, and I eat this apple, in order to burn all this apple, I need to raise this apple up and down 200 times, because 200 times means 200 joule lah. So when I do it 200 times, then the calorie that I consume will be burned lah. So that's what does it mean by joule, the feeling of how much is the joule. So that is the Joule lah. I think that's enough lah kot for Joule. Okay, so that's Joule. So you get some idea about what is Joule. What is Joule? So now about the current. So now about the current. So what is apa kali macam ni? So what is the current itself? Okay, so the current is just simply how much Coulomb. Let me put. It's basically how much Coulomb charge is how much Coulomb macam ni je dia. Coulomb. It's okay lah. How much Coulomb charge pass per second. How much Coulomb pass per second. So that's basically current lah. So meaning that if you have, for example, 1 ampere, if let's say current is ampere, so this ampere the unit. So let's say you saw something said that 1 ampere, so meaning that you know that there is 1 coulomb of charge passed in 1 second, and you know 1 coulomb is basically a million of electron pass some region. For example, let's say this wire. So you know for 1 ampere, if let's say the current flow in 1 ampere, so meaning that you have 6.25 million electron move somehow in 1 second. So that is basically 1 ampere lah. So if I have, for example, like this battery, so this battery, if I put here, nampak lah. So that battery, so I bring you here, so I bring you there. So this battery, if you look on top of this battery, it says 6 volt. 6 volt. So this 6 volt meaning that you have it will give 6 joule of energy every time it's passed through lah. 6 volt meaning that 6 joule of energy every time 1 coulomb is passed. So that's basically volt lah, because we learned before 1 volt is basically a potential energy. Here, this potential ni lah. Saya nampak macam ni, saya buat kecil sikit lah. Takut tak nampak ni, saya kecilkan sikit. Wait lah. Macam ni lah. So you see there, this 1 volt, if you look at the top here, when I said 1 volt is equivalent to 1 joule of energy for every 1 coulomb pass. So this is 6 volt, meaning that you have 1 joule of energy pass when every 1 coulomb. I mean, you get 1 joule of energy every 1 coulomb pass through this battery. So that's what does it mean lah. Okay. Nampak sini nampak sini. Sini sikit. Okay. So you can check this thing. I mean, you can have something like this multimeter in order to check lah. So you have this multimeter. You can hear me or not? Because my mic is over there. You can still hear me or not? You can still hear me?
Yes.
Okay. So basically, so for volt, so this multimeter, so you just go to volt. Where is volt? Where is volt? Oh, this volt. Okay. So no need to know how to use this thing. Just volt is here, there. Okay. So basically, that's, you can see 0, 0, 0, right? So if I go there and I go there, and then you get this, what we call let's do. Okay. So that is basically 6 lah. So you get negative there because the polarity is different. Because if I put the red here, then you get 6 lah. If I put red here, then you get 6 lah. Okay. So in what we call in electricity, when you deal with the electric circuit like this, normally the positive part, what is the positive part? The red positive part, the positive, when you read any electric diagram, the normally the flow of electric is from positive to negative. If let's say you have this diagram like this, so for example, this you have what we call this battery. So this is positive, this negative. So when you draw the diagram, so it's basically like this. So you get this positive. It's positive, right? Negative, right? Yeah. So that, yeah, is it like that? I don't remember. Wait, electric circuit diagram. I think that's correct lah, but let me check first. So I have this positive. How they know it's positive, negative? So you see here. You see here. You cannot see there, right? But basically, if I remove this thing, you can see over here. If I make it bigger, it's low lah. You can see here lah. You can see here. So 9 volt here. You can see the positive, the long one, the long one. Okay, so I think enough there. So let's go back here. Go here, let's go here. So basically you have that thing, the polarity is like that. So if let's say you have like say the what we call the lamp there, so when you read the circuit, so basically you say that the electric flow like this, okay. But you know that the electron is moving, right? So electron is negative, so electron is moving like this. So if you see the electron is moving, because this is negative part, so electron is negative, right? So electron is basically moving like this, but then the electricity, when you read the circuit, is from positive to negative. So this is a confusion because of electron is found after the electricity. So Benjamin Franklin, the Benjamin Franklin, the one that they use the kite, the one that using the kite, and then you have like the lightning and so on. So this Benjamin Franklin, they sort of like formulate the electricity, and they said that the electricity flow from positive to negative, okay, because the existence of electricity, meaning that is positive lah. So that's what Benjamin Franklin think lah. But then the electron is found not during this time. The electron is found 150 years after the electricity, people know electricity. So there are one guy, the name is J.J. Thomson. You can't see, right? J.J. Thomson, but it's okay. I just bring here. So electron is basically found after the electricity. So that's why this the confusion there. So the electron found, and they know that electron have this negative charge lah, negative charge. So by right, the particle of electron move this way, the blue one here, you see the blue one here, like that. But because of this guy, we still use that when we talk about the electricity in general, we talk about the electric move from the positive to negative. Okay, so this need to be clear lah. If not, you'll be confused lah. Why the electron is negative? Why then it start from positive? So it's just because of this guy and this guy. The electron is found later, much later than the electricity. So and they don't want to change it. So that's be it lah. But it doesn't really matter, because when you have positive, it's still correct, because in one way is that electricity, when you talk about electricity, it's not about the electron moving. I mean, when you talk about electricity here, it's yes, electron is moving. But as I said in the beginning of the class, if I say, you see here, in the beginning of the class, the thing doesn't need to be a metal to be conducting. You just need a mobile charge. You just need a mobile charge to get electricity, and you know the charge can be positive, can be negative, and also can be positive. So in case for the electricity, like this, the normal electricity, you use wire is metal, so you have the free electron is moving, so that's charge moving lah. But it doesn't necessarily need to be electron moving. If let's say the proton is moving, especially in liquid, whatever, then it also can conduct electricity. So one way to what we call to synthesize this confusion is that you can view this thing as the positive move here. I mean the positive charge move lah, because when you have negative, you also like the whole is negative. I mean when you have something positive, you also have something negative lah. When you, for example, let's say when the electron move this way, okay, when the electron move this way, meaning that let's say the electron leaving the hole there. So for example, they are like the, let's say this is the atom, okay, the atom, and when electron moving there, so meaning that the electron is like the atom. So let's say the black one is the atom lah, let's say at the beginning, the what we call the electron is inside the atom, right? I mean, let me draw like this. Okay, at the beginning the electron is inside the atom, but when they are moving going to the right. So you, as if let's say the atom like deficient in electron, so we call it hole lah. It's like hole. So in other words, that you see from your perspective, the negative charge go like this, but the hole, they sort of go other ways. The hole here goes other ways lah. It's like when you drive a car along the paths that have a tree. For example, you drive a car. Wait. So for example, when you drive a car, kenapa kat dia ni? For example, when you drive a car and then you drive in the path that have the tree here, let's say you have tree there, you inside the car, if let's say you move forward, you will see the tree is like moving backward. So it's like same lah, like positive and negative charge here. The electron leaving the atom, the electron seems like moving in one direction, but the hole inside the atom seems like moving in other direction. So that's how they sort of like resolve the confusion lah. They said that it's still okay because we just think like the positive charge moving there, although in reality it's the particle, the electron, that is moving other way around. So anyway, just to let you know lah, some confusion about this electricity. Okay, anyway, so you can see there, so that is 5.99, so that is 6 volt. So it's 6 volt there. So if you add, like for example, if you add like the lamp there, okay, so this is volt. You know about the volt, right? So let's talk about the ampere before the current. Let's talk about the current, the ampere, coulomb per second. So if let's say I change this instead of the volt, so this is the volt part. Maybe you cannot see, but just imagine this is volt lah. If you cannot see, this is like a volt part. So if I want to check the current, so I need to sort of do like this. I need to change this thing and then go to current. So if I short circuit this battery, so this basically short circuit lah. I short circuit this battery. So you can see the current. So this current, the reading for current. So meaning that now there are 2 ampere. So meaning that currently but now there are current moving through this thing, moving through this wire with 2 ampere, meaning that for every second there are 2 column of charge moving through this metal lah, through this thing. Every second there will be 2 column of charge, which is the electron in this case, moving through this wire. And 2 column is basically 2 times 6.4, 2 times ni lah, 2 ampere, meaning that 2 times 6.25 million of electron lah. So meaning that for every second inside this wire, you have that much of what we call electron moving inside this thing per second. So that's what does it mean by 2 ampere there lah, 2 ampere. So this is current. Just now is voltage, this is current. And if let's say you put the something in between, for example, let's say I take this, what we call this lamp. So this lamp, and I try to attach to this. Let's say I take this. So I just draw this thing. Macam ni. So let's say I put this thing, and then I just, for example, I just want to to connect this thing with the ni. Okay, so let's say I have this thing. Let's say I just put like this lah. Senang, you nampak kan? Saya harap you nampak lah. So let's say there are no multimeter here. Okay, so if I do like this, you can see the of course lah, the line is goes because it's the complete the circuit. In this case, the voltage is still what we call still 6 volt, but then the current, you can see the current. If I go here, let's say this is the thing, and then I connect this just macam mana ni. Dah buat ni. So if I just bring this to here, and then this thing I connect with this thing. Okay, so now I'm making this thing. So here, if you see the current there, so the current is 0.33. You can see, right? So that thing. So you can see the current instead of 2, now you get 0.3, around 0.3 lah, 0.3 like that. So what I did that just now is basically like this. It's basically when you do something like this, when I have battery like this, and then I connect it with the what we call with the multimeter, it's read 2 ampere. But now when I connect with the what we call the battery, you have this thing, and then I have like a lamp there, and then I connect with the lamp, I connect with the this thing, and then this thing I connect with this. Now is 0.3 ampere. Okay, so they are different there. So what make this different is that as if now, so you see the ampere, so this 2 ampere, this is 0.3 ampere, meaning that what happened is that somehow, let's say this A without lamp, this is with lamp, what happened here, the current somehow become lower, meaning that they are less. So what does it mean here is that less electron moving per second. That's what does it mean lah. So the reason why there are less electron moving in this case with lamp is because the lamp itself act as the resistance. So the lamp here, they act like resistant because inside the lamp you have tungsten. Inside the lamp here, you have tungsten. And if you look at the periodic table, if I go to here, if I go to periodic table, so if I go to periodic table, the tungsten have W. This tungsten, the what we call the symbol is W. So if you look tungsten here, why people use tungsten as a material for filament? If I go to melting point, okay, you can see melting point for the tungsten is one of the highest lah, 3.4 something like that. Okay, melting point, and also in term of what we call heat also the highest. Heat not about heat, it's about electric. Conductivity is not heat, it's conductivity. Electric, it's not about conductivity, it's about this, it's about the melting point, meaning that you can make very thin tungsten wire, but still it's not melting. If you use other wire, for example, if you use iron as the what we call as the if you use this thing, if let's say inside this what we call this thing, you have this thing, so normally people use tungsten lah, because why? Because they have high melting point. Okay, if you use something else, then it will like snap, it will burn before it can glow. Tungsten can stay because the melting point, the electric that goes through that what we call that lamp is not enough to melt the tungsten yet. So that's why people use tungsten, because under the periodic table here you can see tungsten is one of the material that have highest what we call highest melting point lah, something like that. Okay. So where are we? So we go here. Okay, so now there are less electrons, so here you can see there are reduced current because there are less electron moving per second. Because of why? Because the lamp act as the resistance. Okay, so if let's say even though here, no, if I put here, you can see that no, you cannot read, you cannot see. Okay, if I put here, you can, as we see before, is 0.3. You can see that 0.3 like that. If let's say this battery I can vary the current, meaning that I can change the current, and I force 2 ampere instead of here. If you look here, this 0.3, right? 0.3. Okay, I cannot do anything with the with the current because it's fixed. But if let's say my source of battery here, I can change the current. Okay, because there are some meter, something that some device that you can change the current, change the voltage, variable current, variable voltage. If I can force 2 ampere of current through this thing, then the current will be too much for this tungsten lah. It will burn lah. It will, it will be burn lah. So that's why if you have some most of the electrical appliance, they have this current rating lah. So if you give more current than it should, than it need, then you somehow blasting a lot of electron in one go to that particular electrical appliance, and because of that the heating happen and so on, it will be burned, the fuse will be burned. So that's why here is okay because it's not a variable current, so the current it just goes down by itself lah, because this act as resistance. But if let's say you can force the current, then if you give 2 ampere of current, then this thing will be burned lah. Okay, so that's the thing. Mana ni? Saya nak pergi sini. Okay, so let's go here. Okay. So we learn about the voltage, we learn about the current. Okay, so now about the resistance. About the resistance. What is the resistance? Resistance. Okay, the resistance just the inverse of conductivity. Resistance here, resistance is just inverse of conductivity. So this is the symbol of conductivity. Conductivity. We learned in the last class conductivity. We learned in the last class when you see the periodic table, you can see here there are conductivity, right? This thing, conductivity electric. Okay, so you can see certain material can conduct electricity well. So resistance is just the inverse of conductivity. Okay, so if you inverse this, so for example copper, if let's say you inverse 1/59, so here there are 59, right? There are 59. So so if let's say you inverse that thing, you inverse that 1/59 is what? 1/59, you get 0.01. Okay, 0.01. So that is resistivity of the copper. But if you look on the non-metal here, you can see it's very, very low, right? It's very, very low, 0.0001. So meaning that they are very low. When you divide something, when the numerator, when the denominator is very small, then you get the high result lah. So for example like this, for example if you have something like copper, not copper lah, anything lah. For example, let's say you have conductivity of A, let's say 10, B is 1000, B is maybe 0 point something lah, B is 0.001. So let's say the conductivity is that. So it means that the B cannot conduct electric well. It's a pure conductor lah. But if you talk about the resistance, it's just the inverse lah. Resistance. So you can see that the A is basically 1/10, so 0.1 lah. So B, so 1/0.001, so you get 1000 lah. 1000. So in terms of resistance, the B have more resistance than the A lah. So just to show you that resistance is just the inverse of conductivity lah. But it's not as simple as that actually. It just you need to also include the what we call the length. So this the length. So this we call resistivity. This not resistance. This is resistivity. Resistivity. When you want to talk about resistance, you need to talk resistance. You need to include into account. You have this thing, the one that you see before, and also you need to include into account the length and also the area of the material. The length and area of the material. So that is resistance lah. So what does it mean here? It means that if let's say you have a wire, let's say you have this wire, and then you have this what we call the lamp, and then you have what we call the battery there. Let's say you have the battery there, and then you have the lamp there. So if let's say the what we call this thing, let's say you have a thicker one. So if this thing, if the wire is thick, meaning that the area is high lah. When the area is high, the resistance will be low lah, because you see this the equation. When the area is high, the resistance is low. When something don't resist, then the electric can flow very well lah. So you get a higher conductivity. And also if let's say you have something like this, and then you have very long this thing, very long wire, then you can see this thing, the L over A, so 1 over this thing, and then resistance. So you can see this thing, this L is higher. What does it mean? The resistance will low. So when resistance will high lah, because it's proportional, right? It's proportional. So the resistance will high lah. Resistance will be high. So that's why the longer the cable that you use, the more what we call the poor the electric flow lah, because longer wire, meaning that higher resistance. When you have higher resistance, meaning that the electron cannot flow as fast as before, and that cause you have lagging, like in whatever this thing lah, lagging, or maybe the if you use lamp, then maybe the lamp will not be brighter than before. So that is the what we call the relationship between resistance, conductivity. So this thing is conductivity, conductivity. Let me draw in the color. So this is conductivity, this conductivity, okay, conductivity. So you have resistivity, this is resistivity. You have resistance, this is resistance. Let me write nice a little bit. This is resistance. Okay, all this is the properties of material. All this is property of material. We are talking about the electrical properties of material. So some material can resist, some material can have high resistance, some material can have low resistance, and so on. So this is the formula. If the material is long, then it have high resistance. If the material is, for example, have thicker, if you use a thicker wire, then the resistance will be low, meaning that the conductivity will be increased. Okay, because resistance and conductivity, if you look here, resistance and conductivity is inverse with each other. So that's the what we call the resistivity and the what we call the resistance lah. And I said before that the material doesn't need to be metal in order to conduct electricity, because if you think about it, why then people said that don't touch the switch with the wet hand? You know, right? For example, in your, let's say, go to bathroom, you have the switch there, so why not you touch the switch with the wet hand? Let's say the hand is wet hand. Why don't people say avoid touching the switch with the wet hand? If you think about it, the wet hand is made from water, H2O, right? Water. So if you look at the water itself, you go to periodic table, go to water. So the conductivity of the water, so this conductivity of water is itself is non-metal. See, water is non-metal. Let me, macam mana nak buat color ni? Macam nak tu balik? Macam mana nak buat? Saya tak tahu macam nak go default ni. How to go default? The color, the normal color. I also not sure how to go to the normal color. Let me go up and then properties, electron, properties. Macam nak buang ni? How to, because I just want to show. Macam mana nak buat color properties tu? Discovered. Anyway, you can see here lah. Okay, so you can see here they are metal and also they are non-metal. Okay, in the periodic table you have the metal here and also non-metal. On the non-metal, you have oxygen and also hydrogen. Water is made from the hydrogen and oxygen. But water can also conduct electricity. So it doesn't need to be metal in order to conduct electricity. Okay. It turns out why water can conduct electricity is not because of the water itself. It's because something inside the water. It's because it turns out that what inside water can influence influence the conductivity lah, conductivity. Okay, for example, if you have pure water, let's say you have pure water and also pure water, for example, like distilled water lah, distilled water versus normal water versus tap water. Let's say you versus tap water, which one is more conductive and why? Okay, so if you go to this what we call Google, you just Google water conductivity. Let's say I put here water resistivity lah. Normally we call water resistivity, water resistivity. Okay, how much water can resist? Okay, so you look here. Okay, pure water, you can see here, pure water, they have like very high resistivity to 20 whatever million lah, is high. Tap water has very low lah, very low resistance. So this resistivity, how much water can resist the electron flow, meaning that the higher the resistivity, the poor the conductor it is. Okay, the higher the resistivity, the poor the conductor it is. So you can see here the tap water, if you look here, the tap water have the resistivity around 1000 to 5000 like that. So meaning that compared to the pure water, the tap water is better conductor than pure water. Tap water is better conductor than a pure water. So the reason for that is that it's not because this thing is different. This still water. This also still water. What make this thing different, if you think about it, water is H2O. But what make this tap water and pure water differ in terms of resistivity is that what's inside the water. Because water itself is just H2O, it's just the same thing. But what make the resistivity change is because what inside the water. Inside the tap water, there are a lot of ions, because you know the water flow through your pipes, and they are metal. Sometimes the metal leach out and so on, and maybe the sediment during the process of water sanitization, water processing, they put some chemical and so on. So they create some ion inside the water, inside the tap water, the normal water here. So inside the normal water here, let me draw like this. Inside the normal type water here, so the water that is coming out is basically there are a lot of ions. There are a lot of ions. Okay, so when you buy cocoa, whatever, or sometimes when you buy the deionizer, they will remove all this ion. They will remove this ion. Kowe and so on, I think they put it back. But anyway, there are machine called deionizer, what you call distilled water and so on. So inside this thing, so if you look inside this thing, so let me draw like this. So inside this thing, so here there are less ion. So distilled water, they can also call it as deionized water lah. Sometimes it's not good to drink deionized water, because sometimes the iron, your body need iron, and so on. So some deionized water is not good lah for your health lah. When you buy kowe or cocoa, they are not deionized. They putting the iron back, I think. But there are certain water, they are made from deionizer. I don't know, they are filter, deionizing filter and so on. So when you use that particular machine, the water that coming out, they have very less iron or zero iron. So when they are less iron, Iron is what? The term iron itself is what? The term iron is basically the atom that is deficient or surplus of electron. Meaning that if let's say you have carbon, let's say this is carbon, this is carbon, and then you have this thing, you have what we call electron here, 1 2 1 2 3 4. So this carbon. So if let's say this one electron coming out, so the carbon, we say the carbon here, if coming out, the carbon become carbon positive, because the electron is coming out. Okay, so this is carbon positive lah. Carbon is not Ca. Carbon is C only. Ca is calcium. Okay, so that's basically what does it mean by ion. So when the electron goes out from the atom, so the atom have less electron than normal. So when that happen, we call it ion lah. That atom become ion. It's also the same thing if let's say you add more. For example, let's say the carbon here. So let's say the carbon here, the same carbon. So normally carbon have 6, 1 2 this thing, 1 2, and then you have 1 2 3 4. Normally carbon have 6 electron, 4 in the valence electron. But let's say there are extra electron here. Let's say there are extra electron coming here. So now the carbon become carbon negative. Okay, so these two things we call it what we call ion lah. Ion of carbon. Normally carbon doesn't have ion. No, this is not good example, because carbon normally covalently bond with something. I think I should use the better what you call better example. I think maybe calcium. Let me see, calcium is what? Calcium is, this banyak. Lithium lah. Lithium is senang sikit. 2-1. Hydrogen lah senang. Hydrogen nice. Sodium also. Sodium 281. Sodium lah. Sodium is you normally. So this carbon is not really good example. So maybe sodium. Sodium, the Na. So Na have this thing. 1 2 3. So you have 1 2 here, and then you have 8 here, 1 2 3 4 5 6 7 8, and then you have 1 here. So here in the neutral atom, so this sodium atom, natrium is also sodium, sodium atom. So if this thing coming out, so you get what? Natrium plus. Okay, natrium plus. If let's say the same thing, let's say I copy this thing, Ctrl C, and then I Ctrl V. So, but suddenly, let's say now, instead of this thing, there are some electron coming in. So, you get natrium negative. So, this what we call the ion lah. The ion. Okay. So, why I don't use this thing? I said this is quite wrong. Because, not quite wrong, meaning that it's rare for the carbon to become ion. Because carbon normally connected with other thing with what we call with covalent bond. So it's quite rare lah for the carbon. So much better example if I use this small element like sodium. So that's iron. So when you have iron, you see there, when you have iron, either positive or negative. So we know that when things have positive and negative, meaning that they have charge. So we learned about charge before. So we know that they have charge. And we know when you have charge, when you have mobile charge, you can conduct electricity. So that's what make when you what is the reason why people tell you don't touch the electric switch with the wet hand, because of this. Because in the water, in your bathroom, the water is maybe not pure, so there are iron inside that. So if you touch the switch, so there will be conduction, there will be the charge the positive or negative can complete the circuit lah, can flow into the electrical appliance and electrocute you. It will make you ni lah, electrocuted, like that. So that's basically why you cannot say that only metal can conduct electricity. Metal, yes, it can conduct electricity because they are free electron. They are good conductor, fine. But it doesn't mean that non-metal cannot conduct electricity. Okay? Okay, you may say that, okay, this sodium itself is also metal. Right? You might say that, okay, you may say that the water, this water, you have the positive or negative, you have the ion inside that. That what make the, what we call, the water conduct electricity. But it's not the water, but it's the ion. The ion itself is the metal. You might say that. But if you think about it, carbon also, if you think about it, you might argue like this. You might argue that, okay, water is H2O, but the ion inside that give electricity character or conductor character, maybe conductivity character, give conductivity. You might argue like this. You might argue that the water is still H2O, but the ion inside that, and this ion is metal. This ion is metal. That's why the water can conduct electricity. You might argue like this, but still there are some non-metal that can conduct what we call electricity. For example, carbon. For example, carbon. If you look here, if you look at the periodic table, carbon is non-metal. If I click here, metal, non-metal here, right? Non-metal, and so metal there, non-metal there. So you can see carbon is non-metal. Okay, carbon is non-metal, but carbon can conduct electricity. For example, if I do like this, for example, you see this thing, I have this thing. You can see the what we call is ni, right? The thing, what we call the mana? Okay, conduct electricity. So if I have this what we call, let me make it bigger lah. Susah lah saya nak gerak. Kalau you depan saya senang. Macam ni senang. Macam ni. So you can see, so here the wire conduct the electricity, the electron inside the wire, right? Okay, so now you know the pencil. The pencil have carbon, carbon, lead. It's not lead, because lead, if you see lead here, lead is not plumber, it's carbon. This carbon graphite. So if I go like this, put like this, susah ni macam ni. Put yang ni, and then I connect it, and I connect the back. Susah macam ni. Sekejap. Susah Sekejap. So I connect this thing. I don't know whether I can. Buka ni susah banyak sangat wayar. Buat macam ni senang. Conduct. Macam saya buat ni. Kamu apa? Susah belakang ni. But I can conduct lah. So because they are not really what you call, they are not really easy to reach this carbon. But if I can reach this thing, you can see it's conduct electricity lah. So for example, if let's say I have this carbon lead, I don't know why, because it's so small. But it's quite like this, I think. Yeah, you can see that this is a pencil lead from this 2B. So that is graphite. That is graphite, carbon, pure carbon. So if I do like this, and then I connect this thing like this, you can see they are what they call, they are lamp is open on. So showing that this thing is carbon, and you see carbon before is what we call non-conductive. Carbon is carbon is non-metal, but it can still conduct electricity. So this apa benda macam ni? Carbon still can conduct electricity. Okay. Now you cannot say use the same argument as before, like with the water, because you may say the water is not conduct, but the iron inside the water that is conduct. But now when we talk about the carbon here, this carbon, the graphite, is a pure carbon. They are nothing else. They are pure carbon. So how come non-metal like the carbon can conduct electricity? Okay, how come that's happened? It's just because the structure of the carbon itself. If you see the carbon, graphite, especially graphite, graphite. So you have, if you see the graphite, the structure is like a chicken wire like this. It's like a chicken wire like that. Chicken wire like this. So that is graphite. Okay, and then there are another chicken wire like this. Chicken wire like this. Like chicken wire lah. You know chicken wire? Pagar nak pagar ayam tu, dia macam chicken wire. So this is graphite. So you have carbon here. So you can see one carbon is connected with what? With 3. 1, 2, 3. Normally in organic chemistry you see carbon is connected to 4. But in this case the carbon is connected to 3 carbon, not 4 carbon. So when you have 3 carbon, so it's like this. You have this carbon. So you have inside, you have outside, and then let's say this electron 2 inside, and then there are 4. 1, 2, 3, 4. So if this carbon connected to what we call to 4 electron to 3 other carbon, so it will like this. It will like this. So this will be like this. It will be like this. It will be like this. So let me put the different color. This thing. So it will share 1, 2, 3, 4. 1, 2, 3, 4. It's like that lah. It connect like that. And also it's also connect here also. It's also connect here. So you have something like this. And also you have 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 4, 5, 5. Yeah, like that. And then another one, you have something like this. Alah, susah. Okay. Okay, this is the thing like this. So I need to make it bigger lah. So let me make it bigger. How make it bigger? Okay. So let me make it bigger like that. So you have that thing, and then you have another one here. So let me draw another one here. Something like this. Then you have something like this. Like this, and here you have 1, 2, and then 1, 2, 3, 1, 2, 3, 4 here. Okay, so if you look here, this carbon in the middle, you can see you have 1, 2, 3, 4, 5, 6, 7, right? So this is covalent bond lah, sharing the electron. I don't go in detail because this is organic chemistry, so you know the covalent bonding. So this is covalent bonding. So you can see the carbon in the middle sharing with the other 3 carbon in the side. So when you share, you can see the red and green one. You have 1, 2, 1, 2, 1, 2. You have 6, and then you have another one 7. So it's not fulfilled the octet yet. So when this happen, this thing is free to move. This different color lah. This thing is free to move. This electron is free to move. So meaning that in the chicken wire, in the graphite structure, there are electron that is free to move. There are electron here. They are free to move in between this thing. Okay, because between these two, the what we call, this is a van der Waal interaction. Interaction meaning that the weak interaction lah, intermolecular force interaction. it's not covalent bonding. The covalent bonding is here only. The covalent bonding is here only. The one in yellow. This is covalent bonding. But between the sheet, between the sheet, they are not covalently bonded. They are just on the wall. That's why when you have this pencil, you can write on the on the paper, because the structure slide each other. That's why you can write with the pencil, the carbon here, because this carbon is graphite. So when you write, it's like sliding. The top one slide the bottom one. Imagine there are a lot of layer lah. I mean, it's not 2 layer only. There are many layer of graphite, many layer of graphite making this thing. So when you write, the layer will be slide each other. So that's why you see when you write on the paper, you can see the graphite left on the paper. Okay, so that's about the properties of graphite, the sliding between the layer. But what I want to show here is this thing, the electron, the free electron can move, because there are free electron here. So when the electron can move, as you can, when you learn before, the electron is delocalized, then you can conduct electricity. That's the reason why you can use this graphite, this thing, this benda ni, lead, this pencil lead. It's not lead, it's carbon. Lead tu nama je, carbon, because lead also one of the ni, if you look here, lead also one of the, what is lead? Lead plumbum ke? PB, mana PB? Ni PB. If you look PB here, PB, lead. This is not lead, this is carbon. Although they call it pencil lead, lead is another element. Okay, so looking here, if you look here, this is what make the carbon, the graphite is conductive. So this carbon conductive. But also you need to also see also diamond also ni. Diamond, if I put here diamond. Let me draw diamond like this. Diamond. Okay, diamond also carbon. Diamond also pure carbon. Graphite also pure carbon. Let me draw the pencil supaya nanti you ingat. Okay, the pencil. Okay, graphite and diamond both are pure carbon, but diamond is not conductor. Diamond is not conductor. Why? Because the structure of diamond is totally different than structure of this. Diamond, the structure, saya pun tak kerti lukis lah, tapi Google je lah, senang. Macam mana diamond punya structure, diamond atomic structure, diamond structure. Tak kerti lukis the 3D. So let me go here. Mana ni? Okay, so this thing. Okay, you can see that thing. So that is diamond structure. So the diamond, you can see all the atom here. One atom is connected to 4. If I go here. Okay, so let me see there. So one atom of diamond connected to 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. One atom, one carbon atom of diamond connected to the 4. For what you call? For other carbon atom. So it's rigid. It's like 3D network. So there are no leftover electron. I mean that it fulfill the octet very well. So there are no free electron move. So that's why diamond is insulator. It's not conducting. It doesn't conduct electricity. But the what we call the graphite conduct electricity because of the difference of ni lah structure. So the structure in the material matters. The structure in the material matters. So you see lah why diamond is not conductor, because the carbon atom tightly covalently bonded in such a way no free electron possible like that. So that's why the carbon, even though it's pure carbon, the diamond, even though it's also carbon, is not conductor. So you can see the effect of structure in material. Both are carbon, but one can conduct electricity, one cannot conduct electricity even though they are same carbon, pure carbon. Okay, for water you may argue that the metal ion inside the water that cause this thing, but even there are no metal also, even there are no metal, they still can conduct. Even there are no metal ion, like a pure water. Pure water, if you see before, there are resistivity, but still it's not like infinity. The resistivity, they are still numbers, meaning that there are some possibility of conducting the electricity, because the water itself, if you see the H2O, this the oxygen and then the H, apa kali macam ni, oxygen dia macam ni. So H2O, this is oxygen, and also this is the hydrogen. So this is water, H2O. So this thing, even this, you can see they are partial negative. So you can see this thing, this negative, this positive. There are some charge. There are some charging lah. This positive. There are some polarity there. So you have like the imbalance of charge. And we learn about in electrostatic, what we call electrostatic chapter part. This imbalance of charge can also cause some electricity, although not as strong as normal electricity, but still there are some polarity happen. The water can attract it. So that's why even though you have pure water, try not touch the electric appliance, because it might electrocute you. Okay, even though the probability is much lower compared when you use tap water. Okay, because in tap water there are a lot of ion that's promote more electricity lah, more conductive, it become more conductive. So that is basically here. So now 9:45. So yeah. Okay. What I want to do? Okay, last thing. No. So I need last. I think I'll continue later lah, because it's already 9:45. If not, yeah, I continue later lah. Maybe one more class on this fundamental, because even though I say this fundamental part, but we talk also the properties of material. For example, here the carbon, the properties of structure, the effect of structure. So I put the effect of structure, the effect of material structure. So that is effect of material structure. And also we learn about what? We learn about the charge, what make electricity happen. We learn also about something about electricity, the resistivity, resistance, and so on. Please remember this, because I will talk a little bit more about this resistivity and conductivity in the next class. So because I cannot finish today, so I will talk about this resistivity and conductivity. So please study them again about this. And then we talk about Coulomb, we talk about Newton, we talk about Joule, we talk about electric potential. Yeah. So the main takeaway for this class is that it's not electron that make electricity happen. Electron is only one part of story. It doesn't need to be electron in order to get electricity. You can also have proton. So the key is that it's the mobile charge that cause this what we call things moving lah, mobile charge. The mobile charge, and the charge can be positive and negative. If negative, then electron, then positive is proton. The reason why you always associate electron to the electricity is because when you talk about the electricity, you always talk about the metal, wire, metal, and so on. That's why people always associate electricity with electron, but it's not necessarily B, because as you can see before, it's about mobile charge, and mobile charge can be positive and can be negative. If you look below here, it can be positive, it can be negative. For example, if you have sodium positive here, sodium cation here, then you can still make the thing flow lah. I mean, they are like gradient, because whenever you have positive, normally you have the negative. Like I said before, in this case, like I said here, whenever you have positive, whenever you have a negative, for example, in this case, whenever here the atom, when the electron move forward, then the hole will left backward. The hole is positive lah. The hole is basically deficient in atom, is positive charge lah. So basically is happen together. It's like redox lah. Oxidation and reduction is not redox, but basically it's like that. They are two things happen together. Even though electron is moving, we also can say the proton is moving backward. Okay, electron is moving forward. The electron, the proton, the what we call the positive charge moving backward. It's like you in the car, you go forward, you see the tree on the side going backward. So it's happened in one go lah. So I think that's it for today. So let's start with the. I just have one question only. One question. Where is one guy? Oh, Masha or 1, 2, 3 tak pin eh? Okay. Okay. So let's go to the question. One question only as usual. Summarize. I don't want to create a question. I just make things easy. Okay. Summarize. Anyone? Those who open the camera. Summarize. Question time. This is 1 point. Question times. Okay. Summarize what we learned today. Anyone? 1 point. You know 1 point is big, 1 point out of 100. Anyone?
Yeah.
Atira. Okay, Atira.
Today we learn about conductor. We know that metal is a conductor because the electron is free to move, and in element there are like electron and proton, and both have like charge. For electron, the charge is negative 1.6 to the power of 10 to the power of 19, and same goes to proton, but it's positive. The SI unit for charge is Coulomb. The second is we learn about electricity. The formula to count the voltage is potential energy over one Coulomb, because we know one voltage will give 1 joule of energy for every 1 Coulomb pass through. Next we learn about current. It is how much Coulomb pass per second, and we know that you just need a mobile charge to get electricity. And lastly, we learn about resistivity. How to count the resistance is 1 over conductivity. The lower conductivity, the higher resistance. And lastly, we learn about the water. We know that it's not just metal can conduct the electricity, because when you touch the switch with wet hand, you still can kena renjata elektrik. Okay, because the element inside the water will influence the conductivity. Okay. Okay. Lastly, about the effect of material structure, like graphite and diamond. Both are made from carbon, but only graphite can nyalakan electric. Okay, because of the structure. Even diamond also made from pure carbon, but because of the different structure, which is the carbon tightly covalently bonded in such a way, no free electron possible to move.
Okay, thank you, No Atira. So let's take a picture first. Let me here, and then let me bring here. So let me wait. Wait. Let me put here, and then siapa tu? Aida, naik atas sikit. Sekejap. kacau lah. Okay, so let me let's do. Okay, okay, so see the your camera, 1, 2, 3. Okay, okay, so thank you all. So we end our class today with the session of Tasbih, Kafarah and Suratul As.